DJ Mr. Custom!
Let me say yeah.
DJ
Let me say yeah.
Missed the pocket. Yeah, that's something. Our topic of the day is Ohm's Law. Okay, so yeah, this is where we're really going to extend into the world of circuits a little bit more. This is like the gateway into the rest of circuits. I've said that for the past 3 lessons, that this is the launching point. But this one really is. So the first topic of the day is our last big point, our last big topic for before we talk about regular circuits, and that's the idea of resistance. So what is resistance? Resistance is like, it's pretty much what it sounds like. It's something that causes the slowing of the flow of current. Basically, resistance is resisting the flow of current, and this can happen in a variety of ways. Like anything you put in a circuit, like say a light bulb or something, has some built-in resistance. It'll slow the current down a little bit. Or there's like literal resistors that have resistance to them. They slow down the flow inherently, and they're built to do that. So we'll see some examples of how this works in circuits, how this work in circuits later. But yeah, resistance, it's to go to the water analogy, right? Resistance is pretty straightforward. It's just like, imagine you had like some trees or something like laying in the river. It would literally be like slowing the flow, right? If you have stuff in the river, when the water hits it, it slows down and moves slowly through it, right? And if you could make the resistance even bigger, right? You need more resistance to the point where you could even like stop the flow, right? You could have something literally blocking the river. So that's what resistance is like. It's something that's blocking the flow of water down a river or something. That's what resistance is. So resistance has a variable. It's just a capital R for resistance. Pretty easy. But what it's measured in is a little bit more complicated because it's just connected to a sciencey dude again. Resistance is measured in ohms, O-H-M-S, ohms, and the letter that represents the unit is actually the Greek letter omega, but in its capital form, right? Capital omega is what ohms is what you use to represent ohms, not a capital O, a capital omega. Yes. So yeah, that's what resistance is. It's just something in a circuit that slows things down, and we'll talk about why those are necessary in a future lesson whenever I start building some circuits, so we can see stuff. We've got a cool demonstration for that, a cool simulation for that. But yeah, that's what resistance is. And so now we're ready to launch into the big topic of this lesson, which is Ohm's law. Ohm's law is the starting point of circuits and things, and it's a formula. So I'm going to get the whiteboard. And we can write it out. So Ohm's law says that voltage, represented by a capital letter V, is equal to current, which is a capital letter R, times resistance, right? V equals IR. Voltage equals current times resistance. This is the relationship that starts us off on circuits, the big one. But it's a really easy formula, right? V equals IR, really straightforward. So let's take a look at the formula. Let's say we have a constant voltage, just like a battery, right? A battery, a 9-volt battery is the one I used, for example, right? Say we have a 9-volt battery. You can see now, if voltage stays the same, that current and resistance are dependent on one another, right? So if resistance is really small, say 1 ohm, then current would be 9 ohms, right? 1 times 9 is 9. But if, say, the resistance was 9 ohms, right? We've increased the resistance. The current would be 1 amp. Did I say 9 ohms? It's 9 amps. The current would be 1 amp, right? So we increased the resistance. We went from 1 to 9, and therefore it decreased the current, right? It went from 9 to 1. And that follows with our analogy there, right? If we put more stuff in the river, if we resist the flow more, the flow will be slower. So that checks out with our checks and things. The same thing works here with voltage, but it's more common that you're tweaking the resistance in a circuit and not like adding a higher voltage battery. So this really is the more important relationship to look at, the current and resistance relationship. That'll be big later as we look at more circuit stuff. But yeah, this is the simple, straightforward relationship that governs circuits. It's Ohm's law, V equals IR. So let's go ahead and look at the problems. Like, this will make more sense as we use it, right? So I'll erase that, and we'll get into problem number 1, where I get to draw you a circuit diagram, and we get to look at that. Really straightforward, though. So number 1 says, a 10-volt battery is in circuit with a 12-ohm resistor. Omega being ohms, right? What is the current flowing through the resistor? So a little bit to explain here with the setup, but I'll go ahead and draw the circuit. So if you've got the thing printed out, you see the new symbol that we use to make battery, right? It's these two vertical lines, one longer than the other. This is the accepted symbol for a battery when we're drawing circuits. And the way this works is that the big line is the positive side, and the small line is the negative side. Pretty straightforward. The big one is positive always, and the small one is negative. So then we've got our little wires here, right, that connect around, and then we've got that little squiggly thing is what we use. That's the symbol for resistor. Anything that is a resistor looks like that, and then we connect across like that. So that's a very basic circuit drawing, right? This is the battery, plus, minus. This is the resistor. All right, so if this side is the plus, remember we treat current to be flowing from plus to minus, so our current would be going this way around, through the resistor, around, right? That's the way our current's flowing. So the problem says that we have a 10-volt battery, so this right here is 10 volts, and we have a 2-ohm resistor, 2 ohms for the resistor right there. Right, so that's our current, or that's our circuit, and we're looking for our current, I question mark. All right, now, this problem is really, really easy. The setup is there, but I wanted to talk about a few things. Well, like, we see the numbers here, but I want to talk about what's going on before we do that. Think back to voltage. The definition of voltage was it's a difference. It's a potential difference, right? So for this 10 volts here for a battery basically means that there's a 10 volt energy difference between the plus side and the minus side. It doesn't necessarily mean that the positive side is 10 and the negative side is 0. Like, it just means that the difference is there, right? So this could be 11 and 1, because subtracting this would give you 10. It could be 12 and 2, and all that. Those are all possibilities, because this voltage just means the difference between the two poles. But for simplicity's sake, we basically treat it as if the negative side is 0 and the positive side is whatever number it is. So that's how we think about these things, is that the voltage here is 10 and the voltage here is 0. So let's take the question says, what is the current flowing through the resistor? This is a little bit less clear now, but it will be when we start talking about, this will be more clear when we talk about series and parallel circuits, because this is just one circuit. But what's going on here is that the current flows from the positive side around this way, and then it hits our resistor, right? So the resistor is where the current slows down, right? It's the stuff in the river, it's slowing the current down. Now, as the current goes through the resistor, the current is changing, and you're losing some energy there, right? Whenever water would hit stuff in the water, whenever water hits stuff that's laying in the river, right, it slows down. The trees would be absorbing some of the energy, right? The water has kinetic energy as it moves. It hits the trees, it slows down, it has less kinetic energy, right? So the resistors here are doing the same sorts of things. It's absorbing some of that energy, and our energy is dropping as it goes across the resistor. So what is our energy in circuits? Well, it's voltage, it's potential difference, right? So as the current flows through the resistor, we're losing some energy. So there's actually a potential difference across the resistor. There's a voltage drop across the resistor. Um, and that makes sense, right? As you go across the resistor, it would be the current is effectively slowing down. You're losing energy, so there's an energy difference. That's what voltage is. It's an energy difference. So there's a voltage drop across the resistor. Now, what does that mean in this case? How much is that voltage drop? Or how much is that voltage drop? Well, with let's take a look at our battery, right? The battery here is saying that we're treating it as if it's 10 volts on this side, 10 volts, and 0 volts on this side. So whenever electricity is flowing through wires, we treat wires as no resistance, no voltage drop. Basically, the electricity just flows unimpeded through the wires. It's not true in real life technically, but we take perfect cases in physics, right? So the voltage does not change all the way through this wire until you hit the resistor. So it's 10 volts all the way through here, and then you hit the resistor and it's 10 volts on this side, 10 volts. Now, that goes for the other side as well, right? Our voltage doesn't change through this segment right here, and we know that it's 0 volts on the end of the battery, right? So that means that on this side of the resistor, it's 0 volts. This whole area right here, we're treating it as 0 volts of energy on this side. So, what's the voltage drop across the resistor? But it's that 10 volts, right? If it's 10 over here and 0 over here, our voltage drop across the resistor is 10 volts, right? Now, that might have seemed a little bit complicated for this setup, but it's something we're actually going to have to do when we get into those other types of circuits that I was talking about, which would be the next lesson. The reasoning that I walked you through this will be a little bit more clear in the future. But yeah, basically, the voltage drop across this resistor is 10 volts. And that's what we use. We use this setup here to figure out the current that's flowing through the resistor, right? Because we know the voltage drop across the resistor, and we know the resistance of the resistor. So if we use the formula, V equals IR, we know the voltage drop across the resistor, V. We know the resistance of the resistor, R, so we can solve for current, right? So our voltage drop across the resistor is 10 volts. We're looking for current, and we know that the resistance is 2 ohms. So just divide by 2, right? And we get that we have a current of 5 amps. 5, capital A, underline. Yeah, so that's all the current is. Again, very simple math here for me to have drawn out and talked through all of that. But these are the simplified cases, like I've said. So I had to kind of walk you through what's happening in the thought process before we got to the more complicated stuff. Otherwise, it won't really make sense what's going on. But yeah, this is the setup right here. This is what's going on. This will be the basis of all of the things that are going on in the future. Ohm's law is like the cornerstone of what we are doing, at least with circuits. So it's very important that you see what's going on here, but I'll step it out in the future and you'll really see how the other problems break down to this. But yeah, the usage of the formula is really, really straightforward. So let's take a look at number 2, which is our last example, just because there's only so much you can actually do with this basic case. So number 2 says, a resistor and a battery are connected in a circuit. If the 3 ohm resistor has a current of 7 amps running through it, what is the voltage of the battery? So, erase this real quick. So our circuit looks the same here. It's a very simple circuit, so I wouldn't expect you to draw this in the future. But I'll draw it just because we're in our infancy of messing with circuits here. So it's just the battery and the resistor in a circuit. A circuit is connection of electric components. I feel like I didn't define that, but that's what that is. So we know that the resistor is a 3 ohm resistor, and it has a current of 7 amps running through it. So this little arrow is how I represent a current flow. So it's flowing through the resistor. I kind of just naturally drew it from left to right here, but see where I drew my battery with the plus side over here and the negative side over here, and that does mean the current is going, I always get clockwise and counterclockwise. This is counterclockwise mixed up. So it's going counterclockwise, meaning the current would be flowing from left to right, right, through this resistor. And so we're trying to figure out the voltage of the battery, right? Voltage of the battery right there. So what we can use, we have enough information to do an Ohm's law. And what we would be, if we plugged these two numbers in here, the 3 ohms and the 7 amps, into Ohm's law, what we would be getting is the voltage drop across the resistor, just like we figured out, just how we set it up in the previous problem, right? So technically speaking, doing Ohm's law with these values does not necessarily give us the battery voltage, but in this case, since it's a very simple circuit setup, right, the voltage here is the same as the voltage here, and the voltage here is the same as the voltage here, right? So our voltage drop across the resistor is the same thing as the voltage of the battery. That again, my carefulness with explaining these things it'll be more clear in the next lesson. But yeah, so figuring out the voltage drop across this resistor is the same thing as figuring out the voltage drop of the battery. So we can solve it just using V equals IR, right? V equals IR. Ohm's law. So we have voltage is what we're looking for. Our current is 7 amps, and our resistance is 3 ohms. So just 7 times 3 is 21, right? Voltage equals 21 volts. 21 volt battery. There we go. Easy as that. So yeah, these problems, super simple setup. Just wanted to nail that idea home, that voltage equals current times resistance, and you're solving for the voltage across a single resistor with V equals IR, not necessarily a whole circuit unless you've got a good setup for that. But again, we'll make that clear in the future. So yeah, that's all that I have for this one. I'm excited to get into the wider world of circuits in the next lesson, because circuits really work like a puzzle, and they can be really cool for some people if you like little thought math puzzles, which I understand could be not fun for some people, I guess. But circuits are generally well liked because it's more of a thought puzzle than it is a math problem, and people like those thought puzzles more than they like math problems. So I'm excited for that. Looking forward to it. So you should be excited too.